All right, and with that, morning everybody. Welcome back to Complex Analysis, end of week 1, where we will reach the 1/3 point in the semester. Plan for today is we're going to transition from talking about limits and continuity of complex functions to talking about derivatives. So today we're going to talk about what does it mean for a complex function to be differentiable. How our derivatives in the complex plane behave similarly to Calc 1 derivatives, and then the second half of the class we'll talk a little bit about how are they different from Calc 1 derivatives. So, hi Sarah, hope you're doing well too. See you on Monday. Does anybody have any questions or comments before we get started for today? So 2.3, 2.4 in the book. Don't forget to do all the homework set due today. I can't do office hours this afternoon, so my next office hour will be on Monday, 1 to 2. And I put up a new homework assignment, homework 5, which will be due Wednesday, along with homework 4 due Tuesday. Nothing due tomorrow. All right, I've already broken my promise to you, and I'm more than 2 days behind on grading. Translation 2 weeks at this point. I haven't graded the homework 1s yet. Plan is to try and get all grade homework 1, 2, and 3 over the weekend, though. Which, considering there's only 5 of you, including you, Sarah, should be pretty feasible, I think. Alrighty, why did the Romans always find algebra to be really easy? Because whenever they had to solve for x, they were always able to get x equals 10. Roman numerals. All right, so so let's talk about derivatives. So definition of the derivative is basically going to be the same as probably what you saw in Calc 1 once upon a time, with the only difference being we're swapping in z's instead of x's. So we're going to say that f of z is differentiable, and point z naught if f prime of z naught, we're going to define to be limit as delta z approaches 0 of f of z naught plus delta z minus f of z naught all over delta z exists and is finite. So basically the same definition of the derivative as what you likely saw in Calc 1. Calc 1 it was probably written something like limit as h goes to 0 of f of x plus h minus f of x all over h. But that corresponds to the same thing, where h is basic, delta z is taking the place of h. X is just the point at which you're trying to take the derivative, and we're replacing x with a z here, or z naught. If we wanted to say f prime of some x naught, we would write it out like that. So, in Calc 1, what did the derivative represent geometrically? Like if I have a function like f of x equals something like x squared, and we wanted to look at the point at x equals 3, what f prime of 3 is. What did f prime of 3 represent?
The slope of the tangent line at x equals 3?
Yeah, it's going to be the slope of the tangent line at x equals 3. Where the whole idea is h is going to be some really small value where to find the slope of the tangent line, at least using the limit definition, you're going to find the slope of the secant line between 2 points at x equals 3 and x equals 3 plus h. And then you take a limit as h goes to 0. You're taking the slope of a secant line between 3 and some other point that's moving closer and closer to just being equal to 3. I've got good news and bad news. Bad news is we're not going to be drawing such easy pictures in the complex plane for what the derivative geometrically represents. The good news is we're not going to be drawing pictures in the complex plane of what the derivative geometrically represents, because that would be very ugly and scary. Because given our troubles of functions from the complex plane to the complex plane are, and I should probably establish here, f is going to be a function that takes in and spits out complex numbers. Given the fact that graphing things in the complex plane is a much more challenging endeavor than graphing functions from R to R, we're not going to be able to come up with quite so simple a geometric explanation for what the complex derivative is. But it's going to turn out that it'll satisfy some of the same properties, a lot of the same properties, dare I say, and as the Calc 1 derivative, but not all. So let's take a look at this. What does h represent in the Calc 1 definition of the derivative? Or what type of number should I say is h going to be?
Real number?
Yeah, h is going to be some real number. And so if you're taking the limit as h goes to 0 on the real numbers, how many directions can h approach 0 from?
Only 2. Or, yeah.
Yeah.
Left and right.
Left and right. You can take a limit as h goes to 0 from the right. You can take a limit as h goes to 0 from the left. Or equivalently, you can take a limit as 3 plus h approaches 3 from the right, or as 3 plus h approaches 3 from the left. There's only 2 directions to worry about when you're taking a limit as h goes to 0 with the Calc 1 definition of the limit. Katrine, if you had to guess, how many directions can delta z approach 0 from if delta z is allowed to be a complex number?
4.
What are those directions?
It'd be like positive and negative of the real component, and then positive, negative, imaginary component.
So in other words, up, down, left, right? Up, up, down, down, left, right, BA star?
Yeah.
That's the Konami code. Incorrect. But close. Turns out, delta z can go to 0 from infinitely many directions. Because while h can approach 0 only from the right and from the left, if you're taking a look at delta z, how many directions can delta z approach 0 from? Well, you can do it from along the real axes and along the imaginary axes, as Katrine pointed out. You can also do it diagonally, along any line with any slope you might want. You might also get a frisky delta z that approaches 0 along the spiral. You can have a delta z that goes to 0. Psych, I'm coming in this way, doing something like that. Moral of the story is, oftentimes when you're looking at like the derivative in Calc 1, if you try and represent that as a limit, you might just take the limit from the left and the limit from the right and see, oh, are the limit from the left and right equal to each other? If so, goody, the whole limit exists. Can't really do that with a complex limit in a complex derivative. But the idea being delta z can go to 0 from infinitely many directions. And for the overall limit to exist, out of our infinitely many directions, Ginger, along which delta z can approach 0, how many of those limits along different directions have to be equal to each other? It's all of them. Holy moly. Also holy moly. So that's a little bit unfortunate. So if delta z is a complex number, what was like the first thing we ever said about complex numbers?
there's, what was it? There's really no such thing as like a complex number being greater or less than another.
Before we said that,
A real plus imaginary component?
it's got a real component and an imaginary component to it, yeah. Beginning of day one, not end of day one. So delta z as a complex number is also going to have real and imaginary components to it. And then any delta z can be written in the form some delta x plus I times some delta y, where delta z is going to be a complex number, delta x and delta y are going to be some real numbers corresponding to a geometric change in the complex plane. With the idea being, if you have some point z naught, you can have some point z naught plus delta z. When we're looking at this expression in the complex plane, can be a point that's different from z naught in both real and imaginary components, potentially. With the idea being that this will be our delta x, bless you. This will be I times delta y, change in imaginary component along the imaginary up vertical direction. And then delta z will correspond to doing both of those things. And it's important to keep in mind with your delta z's, if you're taking a limit as delta z goes to 0, you have to account for delta z approaching 0 along all possible directions, whether it be horizontally, so that the delta y component is just 0, vertically, so that the delta x component is just 0, or some horrible mishmash of the two. Any questions or comments thus far before we look at a specific example here? So let's take a look at the function f of z equals the complex conjugate of z. We proved yesterday this function was everywhere continuous. That was the last delta epsilon proof we discussed as a class before I set you all loose on group activity. Turns out, I also said at the end of class, this function is going to be nowhere differentiable. And what I would like to do is I would like to use the limit definition of the derivative in order to prove that. So, how do we prove a function fails to be differentiable at a point? Showing that a function fails to be differentiable means showing that this limit does not exist. How do we show that a limit like this is going to fail to exist, do you think?
Could we show that any two of its directions are not equal?
Yeah, if you can find any two directions along which delta z approaches 0, where the limit goes to different values, that would be enough to tell us the overall limit cannot exist if the limit as delta z goes to 0 along two separate directions, any two, is not equal to each other. Because in order for this limit to exist, it would have to be equal along all possible directions. So let's take a look at that. Turns out the limit's always going to be different along the horizontal and vertical directions. So if we do that, let's start by letting delta z go to 0 just horizontally. Meaning, if we were to look at this vertically, we're looking at a value of delta z, where delta z is just going to approach 0 along the real and imaginary axes. So here's a question. If we were to write out delta z as having a delta x component and an I delta y component, which of these, if delta z is only going to be approaching 0 horizontally, which of these two components, the delta x or the delta y, is always going to be 0 along that direction?
Delta Y.
Delta y is going to be equal to 0. So in this case, we can just set our delta z to be equal to delta x plus 0I if we wanted to. So let's take a look at that direction. If we look at delta z only approaching 0 horizontally, at some point z naught, where z naught is just going to be some arbitrary point in the complex plane, we're going to get a limit as just delta x goes to 0 of f of z naught plus delta x minus f of z naught over delta x. Or something to keep in mind is that delta x is just going to be a real number, or a complex number with an imaginary component of 0 if you want. Katrine, what's f of z naught plus delta x going to be for this particular function? So in other words, how would I replace this with some specific expression in terms of z naught and delta z?
It would be the z naught plus delta x bar.
Yeah, it's going to be z naught plus delta x bar and f of z naught.
Z bar.
Yeah,
Z naught bar.
z naught bar. Yeah. So here, whatever you're plugging in for f just depends on what function you're looking at. So in this case, the function f just takes the complex conjugate of whatever you put into it. So in this case, f of z naught plus delta x would just be z naught plus delta x, complex conjugate of all that, ditto with z naught. So now what I want to do is I want to use something we proved day one, which is that you can break up the complex conjugate of a sum into the sum of the complex conjugates to get z naught bar plus delta x bar minus z naught bar. Swoosh, swoosh. Caleb, if delta x is a real number, what's going to be the complex conjugate of delta x? Where if you remember, complex conjugate of a plus bi is just going to be a minus bi.
The same thing.
Just delta x?
Yeah.
Yeah, turns out this is just going to turn out to be limit as delta x goes to 0 of vanilla delta x over delta x. Using the fact here that delta x is just a real number. And Gary, as delta x goes to 0, what can we say is going to be the limit of delta x divided by delta x?
Would it be undefined? Or does not exist?
Delta x over delta x is going to be undefined at 0,
Oh,
but not if we take a limit as it approaches 0.
it'll be one then.
Yeah, because you can just swoosh swoosh in the top and bottom. Turns out we're going to get a limit of 1 as delta z approaches 0 horizontally in our derivative limit here. Any questions or comments related to that?
So we have no idea what this function looks like. We just know that the derivative has on the horizontal is 1.
The derivative in the horizontal direction is 1, correct. So if you wanted to sort of take a cross-section of the complex function and only look at slope from the left and slope from the right, which we're going to be doing in the second half of class once we start taking partial derivatives, it's going to have a slope of positive 1 at every single point in the complex plane. Let's see what happens as delta z goes to 0 vertically. So, in general, we have delta z, as a reminder, is just going to be delta x plus I delta y. If we're only caring about delta z going to 0 vertically, how can we rewrite delta z in a similar way to how we rewrote it when delta z went to 0 horizontally, Ginger?
Delta z is going to be 0 plus delta y.
Yeah, exactly. In that case, we can write delta z as just being equal to 0 plus I delta y, or I delta y by itself, if you will. So in other words, in the horizontal case, delta z had an imaginary component of 0. In this case, delta z is going to have a real component of 0 as delta z goes to 0 in the vertical direction. So let's take a look at what f prime of z naught would have to be in that case. It's going to be a limit as I delta y goes to 0 of f of z naught plus I delta y minus f of z naught, all divided by I delta y. Again, replacing delta z in our original definition with just I times delta y. I times delta y going to 0, I would argue is the same as saying that just plain old delta y is going to 0. So we don't really need this I delta y going to 0 in the limit. We can just replace it with delta y going to 0 for simplicity's sake, because if delta y is going to 0, I times that is going to go to 0, and vice versa. Caleb, what is f of z naught plus I delta y going to be equal to if we plug in the function f that we're working with?
Z naught plus I delta y r.
Yep, we'll just have z naught plus I delta y with a big bar over it, and then minus z naught bar all over I delta y. I'll just put this one down here so we can save that for later.
Why do we take away the I for the delta y going to 0?
Just for simplicity's sake, because delta y going to 0 is the same as I times that going to 0. If you have some expression that's going to 0, I times that is automatically going to have to go to 0 at pretty much the same rate, and vice versa. If delta y is going to, if I delta y is going to 0, then delta y would also have to be going to 0. It's just going to make things a little bit simpler a couple steps down the line to do that. Alrighty. So I'm going to break this up again into two separate pieces. Z naught bar plus I delta y bar minus Z naught bar all over I delta y. Katrine, if delta y is a real number, what's going to be the complex conjugate of I times delta y?
Negative I delta y.
Yeah, it's going to be minus I delta y. Using the fact that if you have a purely imaginary number, something like 3i, and you take the complex conjugate of that, you're going to end up with the negative of what you started with, according to our definition of how complex conjugate works. Just replace a with 0 in this formula. Minus z naught bar all over I delta y. So what I think we can do is we can give this the old swoosh swoosh on the z naught terms. And we end up with a limit as delta y goes to 0 of negative I delta y over positive I delta y. Gary, what's that limit going to go to?
-1.
It's going to be a limit of -1. I's will cancel out, you'll just be left with negative delta y over delta y, which is always -1 as long as delta y is not at 0 itself. What did we just discover? As delta z goes to 0 horizontally, our derivative gave us a limit of 1. As delta z went to 0 vertically, our derivative gave us a limit of -1. What does that imply?
The limit exists. The limit doesn't exist anywhere.
Limit exists, cough cough, the limit does not exist?
Yeah, I was gonna say the limit exists nowhere, but that sounded kind of roundabout.
That would work too.
Okay.
Yeah, I would say the fact that the limit is not the same along two separate directions is enough to say the overall limit can't exist, because in order for the overall limit to exist, it has to be the same along every possible direction. Let's write that down. So we can say since the limit isn't the same along all possible directions, f prime of z naught, which we define to be the overall limit as delta z goes to 0 of f of what, z naught plus delta z minus f of z naught over delta z does not exist. And then since z naught could have represented any point in the complex plane, we didn't impose any conditions on what z naught we were looking at. That tells us f of z is nowhere differentiable. Not a single point in the complex plane at which f of z is differentiable. So there you go. A much simpler example of a Katrina and Ginger of a everywhere continuous, nowhere differentiable function than that or monstrosity Weierstrass function that we constructed back in real analysis.
With the infinitely spiky.
The infinitely spiky thing. Turns out, complex conjugate is not an infinitely spiky function. Even if you, it literally just is a reflection across the real axis in the complex plane. Not something that's super spiky if you ask me, but it still is continuous everywhere, differentiable nowhere.
Are there programs that can graph complex functions for you?
There are programs that can do like what we did on Wednesday, which is like, here's a specific set. Over this specific set, graph what set that the original set, the domain, gets mapped to. Like you can certainly do that in like MATLAB or Mathematica or pick your favorite software. Graphing is in the same way that we would graph a function from R to R, where you could see this point maps to this point, that point maps to that point, that point maps to that point. Not really, because programs are not good at making four-dimensional pictures. Like the human. It is a limitation of our pitiful human mind. Unless you wanted to have like one three-dimensional image that like changes over time and let time be like your fourth dimension. But that would just be messy and not really give you any good intuition of what's going on, I don't think. Gosh, you'd have to have one like, oh, we're going to look at a complex variable where the real component is measured by height and the imaginary component is measured by time. Ew. Not very intuitive. I guess it's possible, but not really something you would want to do. Hey, good question though. Any other questions or comments about this example? So, moral of the story, it's kind of harder for a complex function to be differentiable than it is for a real function. In order for a real function to be differentiable, you need this limit here. It's just the same along two directions, left and right, as opposed to infinitely many directions that you can get in the complex plane. That's the bad news. Good news, do you remember all your favorite derivative taking rules from Calc 1? Power rule, product rule, quotient rule, chain rule, constant multiple rule, sum and difference rules. They all still work over the complex plane. So if you flip to the second page of the packet, I'm not going to write these all down on the board. These are all things you've seen before. All your favorite Calc 1 rules for taking derivatives are still going to hold. You just, again, replacing all of your x's with z's. So for instance, if we had the function f of z equals square root of 3z squared minus 1 all over z plus 2. And if we wanted to find a formula for the derivative of this bugger. Turns out, you can differentiate this function in pretty much the exact same way that you would if this is a function from r to r, f of x equals square root of 3x squared minus 1 over x plus 2. So, Ginger, how would you start that out?
Probably the quotient rule.
Ah, the quotient rule. Low, 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 t high. Minus high, d low. Merrily, 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 merrily. Low squared down below. Indeed. Okay, quotient rule gives us that. Katrine, how do we find the derivative of square root of 3z squared minus 1?
Chain rule.
Chain rule. Yeah, because we can write this as 3z squared minus 1 to the 1/2 power. So, how would you use the chain rule on that?
So, derivative of the outside, which would be 1/2, 3z squared minus 1, so negative 1/2. And then times the derivative of the inside, which would be times 6z.
Times a 6z. I like it. Minus square root of 3z squared minus 1. Gary, what's the derivative of z plus 2?
It's just 1.
That one's just going to be 1. All over z plus 2 squared. And if it's all right with you all, I prefer not to have to simplify this. Is that okay?
That's great. Yeah.
There we go. But the point is, the way you differentiated that, there's really no difference from how you would have differentiated the corresponding function of x from r to r. Same function works for in the complex plane. And then if I ask you, so I'm not gonna really be asking you, like, here's a horribly monstrous function. How would you differentiate this? Because, I mean, it's the same as in Calc 1. Doesn't mean we might not use some of these rules to help us when we start defining new complex functions, like how do we take the cosine of a complex number? How do we take the logarithm of a complex number? But all the same rules and techniques still apply for Calc 1. Questions or comments? So, there's a couple new terms that are related to differentiability that's a little bit stricter than differentiability, meaning it's a little bit harder to achieve these conditions than it is to achieve differentiability at a single point. And that's going to be having a function that's analytic at a point, or having a complex function that is entire. So for analytic, we're going to say that a function f of z is analytic at a point z naught if f of z is differentiable at every point in some open neighborhood of z naught. Awesome. So the idea here is you have a point z naught, and not only is your function going to be differentiable at z naught itself, but if your function's analytic at z naught, it also is going to have to be differentiable at all the points close by, meaning all the points in some open disk centered at z naught. So f of z would have to be differentiable at all points near z naught as well as at z naught. And near here just means in some open disk centered at z naught. Dr. Ursula, if a function is differentiable at a point, does that automatically mean it's going to have to be differentiable at all the points close by? Ginger, you're shaking your head.
I don't think so.
Do you have a counterexample in mind?
The complex conjugate.
That's not differentiable anywhere.
Okay.
So that's not going to be differentiable or analytic anywhere.
Yeah.
We'll take a look. Don't worry, you're all right. Today's activity at the end of class is going to relate heavily back to this. Finding something that's differentiable at some points but not analytic at those points.
Are we gonna care what the epsilon is? Like what our disk is that is?
Depends. If we're looking at specific functions, specific examples, we will.
Okay.
If the main reason though I'm defining analytic now is that for the next 2 weeks we're going to be looking at a lot of theorems relating to nicely behaved functions, and our nicely behaved functions are going to be functions that are analytic on some set, meaning differentiable at every point in the set as well as at some open neighborhood around the points. And generally then maybe our proof will make use of having some epsilon to work with, but in general the size of the epsilon doesn't really matter. As long as, you know, it's positive. So if analytic is hard, having an entire function is even harder. An entire function is a function that is differentiable literally everywhere in the complex plane. differentiable at every point z naught in the entire complex plane, meaning there isn't a single point where your function fails to be differentiable. And so what would be some examples of functions from like Calc 1 that you might remember that are differentiable at every single point?
Z squared.
Z squared. That would certainly be, that's going to be differentiable everywhere and have a derivative of just 2 times z by the power rule. What else? What are some other functions, like real functions or Calc 1 functions that are differentiable at all points in the real numbers?
Like cosine and sine.
Ah, sine and cosine. Yep. Those are differentiable everywhere. And it turns out the complex analogs, sine of z and cosine of z, are also going to be differentiable everywhere in the complex plane. We'll prove that in Monday's class. What else? Caleb or Gary, can you think of any other types of functions that are differentiable everywhere other than cosine, sine, and z squared, or x squared, if we're looking at the real case?
The natural log of z.
Natural log is not going to quite work out because it's going to fail to be differentiable at 0.
Oh.
Is z cubed differentiable?
Z cubed as a derivative of 3z squared, which is defined everywhere in the complex plane. Dare I say z to the 4th might also be differentiable at all points in the complex plane.
Yeah.
Say what?
No, I was going to say z to the 4th, but I was like,
Oh, did I steal your thunder?
Similar to z squared.
How about this? 2z to the 4th plus 3z plus 1 will be differentiable everywhere in the complex plane.
So like every polynomial function.
I was just about to ask, what type, so how can we generalize this? Like what class of function is this? Yeah, all polynomials are going to be entire functions. Because you can just use combination of constant multiple rule, power rule, and sum and difference rules to differentiate those and get a derivative that's defined and nicely behaved everywhere in the complex plane. How about negative powers of z, like z to the negative 1? No? Why not?
Because if you look at 1 over x, doesn't it like diverge to negative infinity and infinity like as it approaches 0?
Yeah. Also, this isn't even defined everywhere in the complex plane. What value of z, Gary, is this not going to be defined at?
Z. Or sorry, 0.
It's not defined, z, 1 over z is not defined at z. That feels deep. But yeah, it's not going to be defined at 0.
Yeah.
So negative powers of z are out, because they're never going to be defined at 0, thus they're not differentiable at 0, thus they can't possibly be entire. Although it turns out this is going to be differentiable everywhere in the complex plane except for at the origin, at z equals 0. And it'll have a derivative of negative 1 over z squared. Any other functions? Calc 1 functions that you can think of that are differentiable everywhere? Gary, you mentioned natural log earlier, which doesn't quite work for reasons we'll get into on Monday. But what function kind of goes hand in hand with the logarithm function?
Exponential.
Yeah, exponential functions. And it turns out functions like e to the z, or in general, a to the z if, and I won't talk about general exponentials yet. But e to the z will be another function that's differentiable everywhere in the complex plane. That one we'll look at towards the end of class today, actually. So most functions that are differentiable everywhere over the real numbers are also going to be differentiable everywhere at all complex numbers. There are a few exceptions, but those tend to be kind of nasty and ugly, and I don't want to talk about them right now. Don't worry, you'll see one in your homework. Any questions or comments about entire or analytic functions? These are two terms that we're not gonna talk too much about today, but that are gonna be super important for us in next week when we start proving properties of entire functions or start proving properties of analytic functions, especially once we start doing integration. So, already flipping the page, spoiling yourselves, I see, Katrina. So, we know for real functions that differentiable functions are always continuous. Katrina, do you think the same might be true for complex functions,
Probably.
according to the packet?
Yeah.
Yeah, turns out we can actually prove that if we have a complex function that's differentiable at a point, then it'll also automatically have to be continuous there as well. So let's see if we can prove that. If f of z is differentiable at a point z naught, then f of z must also be continuous at the point z naught. So here's our proof. We're going to start off with f of z is continuous at some z naught. Or not is continuous. We're going to assume f of z is differentiable at some z naught. What condition? Ginger, can you remind me, what condition does f of z need to satisfy in order to be continuous at z naught?
Its limit has to be equal to its value.
Yeah, so in other words, what we're going to need for this proof is to show that the limit as z approaches z naught of f of z is equal to f of z naught. That's what we would like to show. So, Ginger. What would that imply about this limit here? Limit as z approaches z naught of f of z minus f of z naught. What would that limit have to be in order to satisfy this continuity condition?
Would it have to be 0?
Yeah. It's what you would get if you just subtracted f of z naught from both sides of that equation.
Yeah.
And keeping in mind, f of z naught is just a constant.
Okay.
It's assuming z naught is some fixed constant. It's f of z that's going to be changing. So I'm going to look at this limit. Katrina, what's going to be, what real analysis tricks did we have for rewriting something in a way that makes it easier to work with? Other than triangle inequality, we had two other sort of tricks up our sleeves.
Yeah, we can either multiply by 1 or add 0.
We can multiply by 1, or we can add 0. I'm going to multiply by 1. Specifically, I'm going to multiply by the expression z minus z naught divided by z minus z naught. Just to see what we find. Well, turns out we can do that by taking a limit as z goes to z naught by redistributing terms. I guess first of all, I should ask the class, does this make sense why we would expect this limit to be the same as the original? Because if we're multiplying by z minus z naught over z minus z naught, that's just multiplying by 1, which isn't changing the value of the overall expression. If we're multiplying and dividing by the same thing. So I'm going to rewrite this as limit as z goes to z naught of f of z minus f of z naught over z minus z naught times z minus z naught. Just kind of taking this z minus z naught in the denominator here and moving it over to be having f of z minus f of z naught be what's divided by z minus z naught. And we can use a property of limits. We didn't use this, but this is probably something you saw in Calc 1 once upon a time. Limits break up nicely over products. Say that's the same as limit as z goes to z naught of f of z minus f of z naught over z minus z naught times limit as z approaches z naught of z minus z naught. Algebraic limit theorem from the real analysis folks. Caleb, what would you expect the limit as z approaches z naught of z minus z naught to be equal to?
0.
Yeah, because you can just plug in f of z equals z is just a continuous function. Meaning you could just plug in z naught for z here, and you'll get z naught minus z naught equals 0. How about this limit? Limit as z goes to z naught of f of z minus f of z naught over z minus z naught. That look familiar to anyone? Katrine?
Well, not just the definition of the derivative.
Technically not. Our definition had delta z's instead of z minus z naught stuff. But if we look at limit as delta z goes to 0 of f of z naught plus delta z minus f of z naught over delta z, we can say if delta z gets replaced with the quantity z minus z naught, then that just becomes the same thing as limit as z minus z naught goes to 0 f of z naught plus z minus z naught minus f of z naught over z minus z naught, which is the same thing as limit as z approaches z naught of swoosh swoosh f of z minus f of z naught over z minus 2 naught, z minus z naught. It's two different ways of writing out the same thing, which is f prime of z naught multiplied by 0. Caleb. We know f prime of z naught is a finite number and not like the limit going to infinity or anything like that, because we're assuming f of z is differentiable at z naught. So if f prime of z naught is just some finite number that we're multiplying by 0, what would we expect that product to be?
0.
Equals 0. Bingo. And so what does that tell us? It tells us that the limit as z approaches z naught of f of z minus f of z naught should be equal to 0, which is the same as saying limit as z approaches z naught of f of z is equal to f of z naught. And Gary, what does this condition tell us about how f of z is behaving at z naught?
It means the limit is equal to the function.
Yeah, and how can we sum that up more simply? That the function is blank at z naught.
Is differentiable. Or
Not differentiable.
Continuous.
Continuous, yeah, that was, this right here was our definition
Yeah,
of
so I was gonna say,
continuity.
just hit all that.
Say one of these calc words. So this f of z is continuous at z. And there's our proof. Differentiability implies continuity, just like it did in Calc 1. Katrine?
Yeah, so okay, in the original part, that first line, is the f of z naught, is that inside of the limit? Because then at the end it seems like it's outside of the limit.
It technically is,
So,
but you can, alright, fine. You can split this up into limit as z approaches z naught of f of z minus limit as z approaches z naught of f of z naught if you wanted to. And Katrine, what's the limit as z approaches z naught of f of z naught?
just f of z naught.
Yeah, so this will come out to limit as z goes to z naught of f of z minus z naught is equal to 0, and then you can just add z naught to both sides.
Okay.
Sorry, I did kind of gloss over that fact going from here to here, but there's a little bit of limit algebra occurring along the way. Ginger, Katrine, and Sarah. Does this proof look familiar to you at all?
Yeah.
How so? I'm glad someone's was paying attention in real analysis. This is literally the exact same proof as in real analysis that we use to prove that differentiable functions are continuous everywhere.
Yeah, it was the same one that we used in real analysis.
Ah, very good. I'm glad. Sometimes I feel like throwing chalk at a student. Sometimes I hold myself back. Sometimes I don't.
Oh god.
In this case, it's literally the same proof as you could use to prove that a differentiable real function is always continuous. The only difference being, again, we're replacing x's and x naughts with z's and z naughts. Question. Direct this towards my non-real analysis group. Is the reverse true? Does a continuous function always have to be differentiable?
No, didn't we show that with absolute, or not the.
You haven't looked at absolute value of z's differentiability. Yeah, complex conjugate shows that the reverse is not necessarily true. You can have continuous functions that are not necessarily differentiable. In fact, complex conjugate is the ultimate example of that in that it's literally continuous everywhere but differentiable nowhere. So differentiability implies continuity, but not vice versa. Questions, comments, concerns?
Why did we start with f of z minus f of z naught equals the same thing?
Because that allowed us to bring the derivative into play to allow us to show that this expression comes out to 0, and that condition coming out to 0 is the same as continuity. Basically, the whole multiplying by z minus c naught over z minus z naught thing, or as Katrine put it, multiplying by 1. It's sort of a common trick in analysis type settings to rewrite something in a slightly silly looking way, but that allows us eventually to show that the whole thing we want to be 0 is 0 using the one condition that we have, the differentiability condition. If we didn't do that, we wouldn't have been able to get to 0 in the end, or we would have had to find some other way to get to 0, I guess. Anybody else? Well, let's go ahead and take a 10-minute break. Ready to get stopping point right here. Let's come back at 10:11 on this clock. And when we come back, we're going to talk some more about how complex derivatives behave differently from real derivatives by using looking at some of those partial derivative formulas I kind of spoiled for you in class on Wednesday with the whole del u, del x, del v, del y stuff. Hope you y'all remember your multivariable calculus.
I don't.
I don't expect you to.
No.
Don't worry, we'll do a little bit of review first. Doing okay?
Yeah, I had a question for homework 3. How would you graph the absolute value of the argument of z being less than pi over 4? I'm just,
So something to keep in mind, principal argument of z is just a real number.
so it's just whatever the angle is that corresponds with z, right?
Yeah.
Yeah.
So what would that tell us about just principal argument of z by itself without the absolute value? If the absolute value of z is less than pi over 4, what two numbers does principal argument of z have to lie between?
Negative pi over 4 and pi over 4?
Bingo.
Okay.
And so what would it look like if you took only the points in the complex plane whose principal argument is between negative pi over 4 and pi over 4?
Would it be like y equals x and y equals negative x?
That would be where the principal argument is equal to pi over 4 or equal to negative pi over 4.
So everything like shaded between them?
Yeah.
Okay. But that wouldn't be bounded, right? Because it goes off to infinity.
Looks like it. Doesn't look bounded to me.
Okay.
Yeah, because you could just go out forever on the positive real axis and stay in there. Because anything on the positive real axis is going to have a principal argument of 0, which will certainly satisfy that.
Okay.
Yeah, does that make sense?
That makes sense. So then the absolute value would just be between what, 0 and pi over 4, yeah?
Yep.
Because it's only the positives.
Yeah, so these are equivalent conditions to each other. Using the fact that principal argument is a real number, if it wasn't necessarily a real number, then we couldn't make say this double inequality thing holds.
Wait, is that the absolute? That would be the absolute value too, right? It's the same thing?
Yeah, that's the same thing.
Oh, it is the same thing, okay. Yeah,
So I think that's the graph you want for that particular question.
okay, yeah. Could you help me with z minus 1 minus I? I tried to do like, plugging in x plus iy in for z, and then doing the square root of this, but this was like, I don't know how I'm gonna be able to graph using x's and y's like that.
Well, that looks scary.
Yeah, it does look scary.
I think you can do some fancy completing the square with that to make that work out. But let's see if we can do it without relying on the square root stuff.
Okay.
If I were to give you this equation in the complex plane, let's say we have some point z naught, and I want to say, what is the graph of all points whose distance from z naught
Oh,
is less than or equal to 3? What would that look like?
a disk, a closed disk with radius 3. Yeah, that makes sense. Yeah.
I think you could do something similar here without having to break it up into real and imaginary pieces to
Oh yeah.
just pick your z naught to be whatever
Oh, that-
specific
yeah.
point I gave you.
Yep. Oh, that makes a lot of sense. Okay.
Yeah, some of these, there's sort of little tricks like this too, that it's like, if you try and brute force it with let z be x plus iy, it gets pretty hairy, like what you
Yeah.
discovered, but sometimes if you just think about it in terms of like, oh, that's just the distance formula from z to z naught, it becomes a little bit easier to work with.
And I had a question like in our notes, or when we were doing graphing domain and range, we were doing codomain. So the domain is being defined as z is both real and imaginary components here to be greater than 0 or equal to 0.
Mhm.
And then that would be this, right? This is.
Yep, that's the set D I gave you.
So then to figure out codomain, we put in z squared.
Range, you mean, I think?
Or-
Codomain is just gonna be the complex plane, the second copy of the complex plane where all of your outputs live.
Range, right, yeah.
Yeah.
What, we must have gotten 0 is less than or equal to 2 theta, which is less than or equal to pi. Is that what got us this? I'm not sure how we got from here to here.
Sure. So it basically came from looking at the absolute value of what f of z could be and what the argument of f of z can be. And if you look at the work we did here, if you plug z, or well, if you rewrite z as r e to the I theta and you plug that into the function f of z, meaning you square it, we get r squared e to the I times 2 theta.
Okay, yep.
And the idea is if theta is the argument of the points in the original domain,
Yep.
2 theta becomes the argument of the points over here in the range.
Okay.
Basically saying that the angle of all the points in your original set is getting doubled to get to the points over here. And so since here, points have angles between 0 and pi over 2,
Oh, double that at 0 to pi,
bingo.
which gives us that thing. So this is all the range,
Yep.
beautiful semicircle.
Yeah. And then the 16 comes from the fact that points here have absolute value less than 4, right?
Yep.
And if you square something with an absolute value less than 4, you're going to get something with an absolute value less than 16 instead.
Yep.
That's how we kind of produce that graph. It's just by looking at the argument and the absolute value of what our outputs is allowed to be, given our input restrictions.
So basically the theta and the r, right?
Mhm.
For this function.
Yeah.
What were we doing over here?
Oh, I think here I was just listing out the conditions for what's in the domain,
Okay.
and then here's where we were saying,
Squaring the 4.
yeah, how we got from 4 to 16 being absolute value.
Okay.
Does that sort of make sense?
Yeah, that makes sense. I get
Groovy. Gary, how are you doing?
Pretty good,
Holding up okay?
ready to get into the Calc 3 stuff, not the rust off of that.
So yeah, hey, that was the first class you had with me,
Oh,
right?
it
This
was
was
the first
Calc
class.
3, a couple years ago. Goodness, it's been a while. That was the last time I taught Calc 3.
Oh, really?
Mm-hmm. Trini, you holding up okay?
Doing great.
Say you're starting your job on Monday.
Yeah.
Looking forward to that.
Yeah, I think it'll be good.
That sounded interesting from what you were telling me about.
So.
What
just-
job is it?
I'm doing a data analysis internship,
Ooh.
so cool.
On top of complex analysis for hours and hours each day.
Yeah. We'll
Minute.
survive. It's only for 2 weeks.
Fair enough.
You can do anything for 2 weeks, right?
Sure.
Well, I'm only working part-time for 2 weeks, so
I was gonna say working part-time, yeah.
it'll be fine.
Nice, so.
If it's full-time, I think that'd be another story. Here.
You are, right in the nick of time. Alright, everybody doing okay? into the next bit, which is going to be looking at section 2.4 in the book, improving what's called the Cauchy-Riemann equations. I want to do a little bit of review of multivariable calculus with regards to taking partial derivatives. Because our next kind of big theorem is going to rely heavily on this idea of how do you take a partial derivative. So, Katrine, what did it mean to take a partial derivative of a function like this?
You hold one of the variables constant and then just differentiate like usual.
Okay, so like if we wanted to take del u del x, for instance, for this particular function, what would you do?
It would be y squared minus 2.
Like that?
Yep.
So in other words, you're basically treating y as just being a constant and differentiating with respect to x, right?
Yep.
Caleb, how about if we wanted to take this function and differentiate it with respect to y, holding x as, treating x as just being a constant?
You would have 2xy plus 1.
2xy minus 0, because negative 2x is just a constant with respect to y, plus 1. Bingo. Yeah, so whole idea of taking partial derivatives of a multivariable function like this is you're treating one of your variables as being your actual variable. In this case, for del u del x, it's x. For del u del y is y. And then everything else is just treated as a constant when you're doing your derivatives and doing like power rule, etc., etc. So key formula. I'm going to put this on the sideboard so I don't erase it by accident. How do we define del u del x in terms using the limit definition of the derivative? Ginger?
So you do the limit as delta x equals to 0.
That's a good start. I'm
Um,
glad you're remembering all these things from your past math classes.
yeah. Yeah, I don't know how you would like formalize it.
Well, in general, if u is a function of x, you'd say u prime of x is something like limit as delta x goes to 0 of u of x plus delta x minus u of x all over delta x.
Yeah, so you would have u of like x plus delta x comma y minus u of x comma y all over delta x.
Like that?
Yeah, I think so.
I like it. Yeah. It's basically the same idea as using the original just limit definition of the derivative. The only difference is if we're treating u as being a function in terms of like two variables like x and y, we're just going to be adding, when we're differentiating with respect to x, we're going to be adding a delta x to the x component of u and then leaving the y component alone when we're defining our partial derivative formula. And so then, Gary, how would you expect del u del y to behave differently?
It'd be limited as delta y goes to 0, u of y plus delta y, or sorry, x comma y plus delta y minus u xy over delta y.
Exactly, yeah. Same thing, but delta y is getting added to the y component in our sort of difference quotient here, and we're taking a limit as delta y goes to 0. I'm leaving these limits up here because we're going to need these limits here in just a couple of minutes. But is everyone okay with that so far? Oh, what does he write things down? I'll let you do that.
That makes a lot of sense.
I'm glad to hear it. So what I want to do now is remember how towards the end of class on Wednesday we talked about how given a function f of z, f of x plus iy, you can break the function up into something with real and imaginary components. You can break it up into u of xy plus I v of xy. What I want to do now is I want to find a relationship between, if we look at the relation, taking f of z and breaking it up like this, how can we somehow find a way to relate the derivative of f of z? So in other words, how can we relate f prime of z, or f prime of, let's say, some point z naught to u of x naught comma y naught and v of x naught comma y naught. So in other words, how can we relate the overall derivative to the real and imaginary pieces of the function that we're differentiating? In spoiler alert, it's going to somehow involve relating f prime of z naught to these partial derivatives. To these partial derivatives. So we're going to do something like what we did in the first part of class where we were looking at complex conjugate of z. We're going to take a limit as delta z goes to 0 horizontally and vertically, just to see what we can find. So let's say, so we're given this formula here for f prime of z naught. What I'm going to do is, once again, we're going to break up delta z into real and imaginary pieces. Delta z we can represent as being some delta x plus I times delta y. And similarly, z naught, we're going to break up into having real and imaginary components, where z naught is just going to correspond to some point in the complex plane. Y'all ready for this? This is going to be fun. Let's start by letting delta z go to 0 horizontally again. So delta z approaching 0 from the left and the right. Katrine, what did we say about delta x and delta y in that case? If delta z is going to 0 just horizontally.
Delta z will just equal delta x.
Yeah, delta z is going to be delta x. So if we write that out, we can write f prime of z naught then being the limit as just delta x going to 0 of f of z naught plus delta x minus f of z naught all over delta x. And what I want to do now is, instead of writing out z naught, I'm going to break z naught up into x naught plus I times y naught to get a limit as delta x goes to 0 of f of x naught plus delta x plus I delta y, or no, I times y naught, excuse me, minus f of x naught plus I times y naught all over delta x. So all I did here was took z naught and replaced z naught with x naught plus I times y naught. All right, Gary, you ready for this next line?
All right.
This next line's a little bit of a doozy. I'm going to take this expression and break f up into its real and imaginary components. Replace f of complex number with u of xy plus I v of xy.
Why does delta x go to I, y not?
It's because delta x is just a real number. So the delta x is getting attached to the x naught to say this is the real component of what's inside of the f here, and this is the imaginary component of what's inside of the f.
So that's the imaginary component. Okay, I understand.
Yeah, of the z naught plus delta x. Alright. We're gonna break this up into real and imaginary components of f, which is gonna give us u of x naught plus delta x, comma, y naught, plus iv of x naught plus delta x, comma, y naught, minus u of x naught comma y naught plus iv of x naught comma y naught. All over delta x. Like I said, it's a bit of a doozy of a line. But what we did here was we just took f of x plus iy and split it up into the real and imaginary components, both for our first copy of f as well as for our second copy of f. And then Ginger, what you were asking about earlier, why did we split it up into x naught plus delta x plus iy naught? It's that we could get the real and imaginary components of this piece kind of written out separately. Where the real component is x naught plus delta x, the imaginary component is y naught.
Oh, okay, okay, never mind. That makes sense. I was about to ask why there's not an I next to the first y naught and the u of x naught plus delta x.
Yeah, it comes back from over here.
Yeah.
Like when we're breaking up a complex function into its real and imaginary components, we just have y by itself there without the I piece attached. The I piece comes in front of the v. All right, I'm going to rearrange some of these terms. Get a limit as delta x goes to 0 of u of x naught plus delta x, comma y naught, minus u of x naught comma y naught, plus I times the quantity v of x naught plus delta x, comma y naught, minus v of x naught comma y naught, all over delta x. So basically, I took the two u terms and combined and put them next to each other, and then the two v terms I put next to each other and factored out an I from that. Y'all with me so far? These are big, complicated expressions, but we're going to simplify them down to nicer looking things here in a couple of steps. Next step, I'm going to take this monstrosity and break it up into two separate fractions, as well as two separate limits, and get limit as delta x goes to 0 of u of x naught plus delta x, comma y naught, minus u of x naught comma y naught over delta x, plus limit as delta x goes to 0 of I times v of x naught plus delta x, comma y naught, minus v of x naught y naught, all over delta x. So in other words, I took this expression, I broke it up into two separate fractions, and then said, we'll just take the limit of each of those separately. limit of the u fraction plus limit of the v fraction. Y'all ready for the magic to begin? Katrine, what's that limit?
That's just the delta x.
Yeah, del u del x. Yeah, if we look back at these formulas we have over here, right, this is the same thing as what we have written down here, replacing x and y with x naught and y naught. But that just means this expression is going to be equal to del u del x evaluated at the point x naught comma y naught. How about this other limit? First of all, I'm going to take this I here in our numerator. I'm just going to put it out in front as a constant multiple. Constant multiples you can move inside and outside of limits, so that's okay. And Caleb, what about this limit? Limit is delta x goes to 0 of v of x naught plus delta x comma y naught minus v of x naught y naught over delta x.
Del v del x?
Yeah, that's just the partial derivative of v with respect to x at the point x naught comma y naught. So what we find, make a note of that over here, is that f prime of z naught should be equal to del u del x at the point x naught comma y naught plus I times del v del x at the point x naught comma y naught.
Isn't that only the horizontal direction though?
That's the horizontal direction. We're assuming f of z is differentiable so that the limit will be the same from all directions. So if from one direction it's equal to this expression, it should also be equal to that from all directions because we've already assumed we have differentiability. Does that make sense? Cool. So we were able to take f prime of z naught and break it up into del u del x at our point plus I times del v del x. Everyone good? Because we're going to do the same thing now all over again, letting delta z go to 0 vertically. All right,
It's probably gonna be the same thing, just with y's.
it's going to be close to the same thing, but with y's.
Okay.
Not exactly the same thing. I don't want to spoil it, but. So now, delta z goes to 0 vertically. If you're running out of room on the page, I gave you a bunch of room on the next page as well that you're welcome to use as well. So delta z equals delta x plus I delta y. Z equals x naught plus I times y naught. If delta z goes to 0 vertically, Gary, what would delta z be equal to? Or how can we simplify that?
Just delta y, or I delta y.
Yeah, in this case we'll have delta z is equal to I delta y. So if we look at this, what we'll find is that f prime of z naught should be the limit as I delta y goes to 0 of f of z naught plus I delta y minus f of z naught all over I delta y. Again, just taking our derivative formula and replacing our delta z's with I delta y's. So we're okay with just saying we're going to take a limit as delta y goes to 0 instead of having I delta y going to 0, because if one goes to 0, the other has to go to 0 as well. So you write that as limit as delta y goes to 0. And just like we did over here, we'll start by breaking z naught up into its real and imaginary components to get f of x naught plus I times the expression delta y, let's say y naught plus delta y, minus f of x naught plus I times y naught, all over I delta y. And what I did here is if you were to take this expression and multiply it all out, you'll get x naught plus I y naught plus I delta y, which is the same thing as z naught plus I delta y. So far, so good? So now we're going to do the same thing that we did over here. And yes, Gary, that means we're getting an extra long line. I don't want to call you out on this specifically, but I started doing that, so now that's what I'm going with. We're going to break up f once again into its real and imaginary components. Use that f, here we're using that f of x plus iy is equal to u of x comma y plus iv of x comma y. And if we do that, we'll get a limit as delta y goes to 0 of u of x naught comma y naught plus delta y plus iv of x naught comma y naught plus delta y. All of that minus the expression u of x naught comma y naught plus iv of x naught comma y naught all over I delta y. So again, this looks a lot bigger and scarier, but we really just use this formula here to break up f into its u plus iv form, to real and imaginary components. Give y'all a minute to write that down. Oh, while they're writing that down, Sarah, I just realized I forgot to put the del u, del x, and del u, del y formulas where you could see them. Here, look at the very top of the page. There you go. You know, try to be inclusive. All right, Ginger, what do you think our next step's going to be?
I think we're probably gonna collect real components and imaginary components.
Yeah, we're going to collect the u pieces and the v pieces to get a limit as delta y goes to 0 of u of x naught comma y naught plus delta y minus u of x naught y naught plus I times the quantity v of x naught comma y naught plus delta y minus v of x naught y naught. Ooh, afraid I was going to have to barge into the homework 3 due today space. All over I delta y. And then, Caleb, any guesses as to where we'll go from here?
We could, I think we should split up into 2 limits.
Yeah, split it up into 2 fractions and take the limit of each. I like it. That'll give us the limit as delta y goes to 0 of u of x naught comma y naught plus delta y minus u of x naught comma y naught over I delta y plus limit as delta y goes to 0 of I times v of x naught comma y naught plus delta y minus v of x naught comma y naught all over I delta y. Gary, what is this limit on the left going to be equal to?
That should be del u del y plus I del v del y.
Yeah, del u del y plus I del v del y.
Oh,
Almost.
Also evaluated at x naught, y naught.
Evaluated x naught, y naught.
Both of them.
Almost. We have to fact.
Oh,
One thing you're forgetting is we have a 1 over I constant out in front.
Yeah, that's true.
But we can just move that out in front as a constant multiple. That's not a big deal. So we just end up with 1 over I times, I think, what you just said.
Yeah.
So that'll give us, so we can erase this I, move it as a 1 over I out here. We can take these two I's and put that as a I over I out there. Okay, swoosh, swoosh. And then I think what we'll get is 1 over I times del u del y at the point x naught, y naught, plus del v del y evaluated at the point x naught, y naught. Here I kind of took this I in the denominator and moved it out in front of each fraction. Also, this I kind of moved out in front of the limit as well as a constant multiple. So far, so good? All right, we have one thing left I want to do with this expression before we start doing some comparisons. What's 1 over I?
I to the negative 1.
Okay. How do we write that in standard form? What was our trick for doing a quotient of two complex numbers?
Conjugate.
Yeah, let's multiply by the conjugate in the top and bottom. What's the conjugate of I?
Negative.
So in the numerator, we'll get a negative I. What's I times negative I? Yeah, because you can write I times negative I as being the negative of I squared, which is negative 1. And the whole thing comes out to negative I. So what we end up with is negative I times del u del y evaluated at x naught, y naught, plus del v del y at x naught, y naught. And that's from taking the limit as delta z goes to 0 vertically instead of horizontally. Oh.
I was just trying to figure out how I times negative I is 1. But, yeah, that makes sense.
Yeah, if you combine the two i's, you get negative 1 times the extra negative sign you get comes out to positive 1. All right. Houston, we have a problem. Taking a limit as delta z goes to 0 one way, we got that expression. Taking a limit as delta z went to 0 another way, horizontally, we got that expression. If the limit's the same from all directions, what has to be true about these two different expressions I just boxed?
They're equal.
They have to be equal to each other in order for the limit to be the same from all directions and to give us differentiability. So we can say, and in order for the limit to be the same, along all directions, it's going to have to be true that del u del x evaluated at x naught y naught plus I times del v del x evaluated at x naught y naught has to be equal to negative I times del u del x at x naught y naught plus del v del y evaluated at x naught y naught.
Should that first del u del x be del u del y? And the second?
Oh, yeah. Yep. Sorry, a lot of variables to keep track of here.
Mhm.
Del u del x plus I del v del x should be equal to negative I del u del y. Yep. All right. Holy smokes. What do we know about each of the partial derivatives individually? This expression without the negative I, this expression. Where do all of these partial derivatives live?
In the real world.
They're all real numbers. Because if you remember, u and v are both functions going from R2 to R. So the outputs, so the partial derivatives at a particular point should all be real numbers. So what does that imply? Well, it implies that if we set the real plus imaginary components with each side equal to each other, what are we going to get? Gary, what's the real component of the left-hand side of this equal sign?
The del u del x evaluated at x naught y naught.
What's the real component of the right-hand side?
Del v del y evaluated at x naught y naught.
Bingo. We're going to get that del u del x at the point x naught y naught has to be equal to del v del y at x naught comma y naught. And if we set the imaginary components of both sides to be equal to each other, Gail, what are we going to get?
dv or del v del x of xy and x naught y naught equals del u del y of x naught y naught.
Like that?
Yep.
Not quite.
The negative, sorry.
I would say one of these needs a negative sign on it. What did I do in my notes? The negative del u del y. And these two equations right here, we're going to call the Cauchy-Riemann equations. Which are a pair of equations that have to be satisfied for any function f of z that's differentiable at a point. So in order for your function to be differentiable at a point, it has to satisfy that the partial derivative of u, that if you take f of z, and we can write this out as a theorem, which we've essentially just proved, that if f of z equals u of xy plus I v of xy is differentiable at the point z naught equals x naught plus I times y naught, then it has to be true that del u del x at that point equals del v del y at that point, and it has to be true that del v del x has to be the negative of del u del y. That in order to have differentiability, the Cauchy-Riemann equations here have to be satisfied. Ginger.
Were Cauchy and Riemann contemporaries? Like, did they work on this together?
I think, yeah, they were doing math at roughly the same time. I want to say they kind of both discovered these somewhat independently of each other,
Okay.
and then found out that they had the same result and were like, oh, hey, we both came up with this. Let's be best buddies and name it after the both of us.
Okay.
No, I don't think that actually happened. I think it was more like they each wanted it to like claim credit for it, and then future mathematicians were like, yeah, they both came up with it, let's just give them both credit. Riemann, you might recognize as being a name that's often attached to integration, like the Riemann integral is kind of the type of integral that you typically learn in like a Calc 1 class. Cauchy's a name that we're going to be seeing like every day for the rest of the semester. Like we've got, like this is the first of like 5 or 6 theorems that we're going to have that are the Cauchy something 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 theorem. There's going to be a lot of that going on next week. Here's our first appearance, Cauchy-Riemann equations. If your function's differentiable, then its real and imaginary components have to have partial derivatives that satisfy these two equations.
Are we in like C2 right now? Like C2 to C?
Nope, all of this, f is still a function from C1 to C1. It just takes in a single complex number and spits out a single complex number. U and V, though, are both going to be functions from R2 to R,
Oh.
but F is still just going to be a function from C to C. It's just that, keeping in mind that C behaves a lot like R2 in this respect, and that if you take in a complex number as an input, it's going to have a real and imaginary component to it.
So like U of x, y is the real component,
Correct.
but we're splitting it up into 2 variables in a real number system?
Because U we can write as a function in terms of x and y, the real and imaginary components of whatever z is we're plugging in. We can also take v and split it up in the same way, and that sort of gives us a way to take a complex function from c to c, which is sort of like a function from R2 to R2 in terms of the number of components of the inputs and outputs in a way, and splitting it up into one piece that goes from R2 to R and another piece that goes from R2 to R. From R2 to the first copy of R here, and from R2 to the second copy of R here. Well, we'll do an example here in a second where hopefully it'll make a bit more sense. Y'all doing okay? Is it time yet, Katrine?
I think it is time.
Next joke? All right. Why did the mathematician spill all of her food in the oven? It's because she was following the instructions, which just said to put the food in the oven at 180 degrees.
Oh.
So let's do an example of where we actually use these Cauchy-Riemann equations to find where a function is differentiable. And then after this example, I'll give you another break. So you know how the real absolute value function is differentiable everywhere except for at 0? You have a single spike at 0, but everywhere else it's nice and well behaved. If you look at the complex absolute value, complex absolute value is nothing like that. Turns out complex absolute value is nowhere differentiable. It not only fails to be differentiable at 0, but it also is going to be differentiable at no other point as well. So let's show that. And there's two ways we could go about approaching this. We could do like what we did on the front page with the complex conjugate and just take a limit as delta z goes to 0 from two separate directions. But we could also use the theorem we just proved. And by the way, the proof of this theorem is literally all the work we did to derive these two equations in the first place. We can also show that the Cauchy-Riemann equations are never going to be satisfied by this function. So, if we're going to take the absolute value of f of z, z, which is the same as taking the absolute value of x plus I times y, somebody refresh my memory. How did we take the absolute value of an expression of the form x plus I, y?
It's just the square root of x squared plus y squared.
Yeah, that's just by definition square root of x squared plus y squared. What's going to be the real component of that expression, and what's going to be the imaginary component of that expression? If we were to try and take square root of x squared plus y squared and write that as being some real function, u of x, some real expression, u of xy, plus some imaginary expression, I times v of xy, what would our u of xy be, and what would our v of xy be in this case?
Our u of xy would be x squared of x squared plus y squared.
And what would v of xy be?
0.
Indeed. Turns out this function has an imaginary component of 0. Because
Why?
Because our magnitude is always going to be a real number.
yeah, because if you wanted to ask me what's the real and imaginary component of square root of x squared plus y squared, well, square root of x squared plus y squared is itself a real number. It's going to always have an imaginary component of just plain old 0. So
Oh, okay.
this is the u part is the part that's a real number. The v part is the part that's an imaginary number. But since there is no imaginary part to square root of x squared plus y squared, we're just going to get v of xy is equal to 0. If we had gotten something like, oh, square root of x squared plus y squared minus 3i, for instance, or minus 3xyi, then we would say v of xy would be negative 3xy. But in this case, since square root of x squared plus y squared has no imaginary piece to it at all, it has an imaginary component of 0. All right, so we are going to need to take all the partial derivatives of this function. Don't worry, I'll do the hard ones.
Oh, thanks. Really appreciate that. That's helpful.
Yeah, do what I can for you.
Yeah.
All right, Caleb, I'll give you one of the easier ones then. How would we take w del x here? Differentiate square root of x squared plus y squared with respect to x. I'll give you a hint.
Yeah. Would it be x times root x squared plus y squared?
Close. Not x times root of x squared plus y squared. I think it's going to be division. Because if we do chain rule on this, we'll get, what, 1/2 times x squared plus y squared
Oh,
to the negative 1/2,
oh yeah.
multiplied by
2x.
2x. And then the 1/2 and the 2 would cancel out to just give us with x times x squared plus y squared to the negative 1/2, which is the same as x over plus y squared. Katrine, how about del u del y?
1/2 x squared plus y squared is negative 1/2 times 2y, which equals y over the square root of x squared plus y squared.
Basically same thing, just swapping out the x in the numerator with the y. Running through chalk like mad right here. Get a good piece. I don't think it looks stuff. You all ponder this amongst yourselves while I get some more chalk.
What did Cauchy say to Riemann when Riemann said he didn't want to hang out?
What?
Why not?
Are you punning without me, Katrina?
Yeah.
Oh, goodness gracious.
What did you hear?
You just see,
Well, I just came in and heard why not at the end and guessed that's what she was doing.
I was thinking about that for a while.
X not, why not? Yes, oh yes, I think my fair share of puns there. So in order for the Cauchy-Riemann equations to be satisfied, so in order to get del u del x equal to del v del y, what do we need? We need that x over square root of x squared plus y squared has to be equal to 0. Setting del u del x and del v del y equal to each other, which if our function is differentiable at the point xy would have to be satisfied. So if x over square root of x squared plus y squared is equal to 0, what does that tell us about x and or y?
X has to be 0.
Yeah, you can, and y?
And y, does it have to be 0 or what about y?
Does this tell us anything about y?
Oh,
It can't be 0.
It can be, does it have to be?
Well, wouldn't it, if x is 0, then you don't want y to be 0 because you would get undefined.
Yeah, we would have to have that x equals 0 and y is non-zero. Because if x and y were both 0, you would be dividing by 0 and that would be sad. So that's what we get from our first Cauchy-Riemann equation, is that in order for our del u del x to be equal to del v del y here, meaning x is 0, but y is non-zero. How about our other one? Del v del x is equal to negative del u del y. What equation do we get here from our specific function?
negative y over square root of x squared plus y squared equals 0.
Yeah, negative y over square root of x squared plus y squared equals 0. Which tells us what?
Y.
Gary?
uh,
No, sorry to say your thunder, Caleb.
that y is equal to 0. And x has to be non-zero.
Yeah. Y equals 0 and x is non-zero.
Those can't both be true.
Yeah.
Holy smokes. How many points are there in the complex plane where x is 0 and y is non-zero and y is 0 and x doesn't equal 0?
0.
Empty set.
I was gonna say, let's say 0, because 0 sounds like you're talking about the complex number 0, which doesn't satisfy these two conditions. No points in the complex plane satisfy the Cauchy-Riemann equations, therefore,
It's not differential
anywhere.
anywhere.
Big no. no point z equals x plus iy in the complex plane satisfies the Cauchy-Riemann equations, which means f of z is nowhere differentiable. And there you go. No need to look at delta z approaching 0 from multiple directions. We can just take our original function, break it up into its real and imaginary components, find the appropriate partial derivatives, set the appropriate ones equal to each other, and we see that no point in the complex plane will satisfy both of the Cauchy-Riemann equations simultaneously. And since both of these equations being true is necessary for differentiability, f of z is nowhere differentiable. Questions, comments, concerns?
I have a concern that you haven't drawn a square.
Oh, pardon me. Does that make everything better?
I'm no longer concerned.
It's not really a square, it's more of a rhombus. But... All right, in that case, let's go ahead and take a break until 11:10. When we come back, I have one more example I want to talk about, and then I'm going to give you all an activity where you all get to play around with the Cauchy-Riemann equations for a different example. So break for about 7-8 minutes, and be back here at 11:10. What's so fun?
One of my friends is sending me pictures of her smoking cigarettes in Italy.
Oh,
I'm taking
how sophisticated.
while taking a
Sorry.
class in Hillsdale, Michigan.
While you're sitting here listening to me ramble about imaginary
Just like
numbers.
looking over the Italian countryside.
I'm sorry I'm so disappointing in
It's
comparison.
okay, it's okay. You can't,
Help it.
yeah.
I can't help but be disappointed.
Wow.
I mean, come on.
Mm. All right, these equations on the slide. Be back in a minute.
Your teeth are falling apart.
You know. I've tried super gluing them together, but it doesn't seem to be working.
Really? Oh.
Did you try super glowing?
My jeans. Not really. I was just joking. He told me my jeans are falling apart. One time I walked into class with these jeans on, and Dr. Molosov went, "Who ate your pants?"
Who ate? What? Who ate whose pants?
She would say that.
Dr. Molosov said that about my jeans.
Oh, who ate your pants? One of those pants gremlins they have around campus.
What?
One of those pants gremlins they have around campus, huh?
They'll get you.
The family gathering. Like, you paid money for those.
Maybe it was the
Yeah, those-
Sale.
I could have told you those would not meet Dr. Volosov's fashion standards.
Maybe it was Dr. Chor's dog.
Min just gave him one for your
Okay, I
pants.
was thinking about that. Is the reason why they call him Min because everyone called their dog Max?
They have another dog called Max who's bigger.
Do they
Oh,
actually?
really?
They actually have another dog named Max.
That's
Yes.
Oh, wait.
Yeah.
That's
That's
actually
awesome.
so cool.
Max and Min. Oh, it's not as nerdy as one of my good friends from grad school who, believe it or not, actually named his dog, two dogs, Epsilon and Delta.
Oh man.
Oh,
No way.
that's a new level.
Okay, do you know that the movie Up?
Yeah.
I'm pretty sure one of the dogs in there is named Epsilon.
Yeah, I think they just like, I think it's just like Alpha, Beta, and Epsilon or something.
Yeah.
I don't know.
Okay.
So I
Makes
mean,
sense. Alpha, beta, gamma.
And a bird named Kevin. Here's my Facebook profile picture.
But Kevin's a girl.
Doesn't matter. Kevin's awesome.
I'll get $2 to name them that are identical and call them Cauchy-Riemann.
There you go. Gosh. Now, if you really want to do that, name them Riemann and Lebesgue, which are the two different types of integrals. Those are the real rivals of that program. All right. Anyway, let's get back to it. So, question before you flip the page and spoil yourselves. I said before. We said that in order for a function to be differentiable, it's necessary that the Cauchy-Riemann equations are satisfied. Here's my question. Is it sufficient? Turns out the answer is no. But it almost is. Turns out we have a theorem that says if the Cauchy-Riemann equations are all satisfied and all your partial derivatives are continuous at your point, then, and only then, can you guarantee differentiability. So, if f of z is defined in some neighborhood of z naught, and if del u del x, del u del y, del v del x, and del v del y are all exist and are continuous, in everywhere in D. And the Cauchy-Riemann equations are satisfied. At z naught. Then f of z is differentiable at z naught. So in other words, in order to guarantee differentiability, it's not enough that you have the Cauchy-Riemann equations be satisfied at your point. The partial derivatives all have to also be continuous at your point. Spoiler alert for homework 5. Homework 5 has a function on it that satisfies the Cauchy-Riemann equations and yet fails to be differentiable because condition 1 is not satisfied. Partial derivatives turn out to not be continuous. But I'll let you all stew on that over the weekend. So if you have the Cauchy-Riemann equation satisfied and your partials all exist and are continuous, then you get differentiability. We're not going to prove this theorem because this theorem is kind of a nightmare to actually prove. It would take us like a full, probably like day of / week of class to actually prove this.
Wait, really?
It's in the book, it's in the textbook, but it's messy and long and complicated, and I don't wanna.
Wow.
Deriving the Cauchy-Riemann equations, I think, is fun and interesting. Proving this theorem, less so. So in the interest of time, we're gonna skip this proof. Instead, I'm more interested in using this proof to do some examples. For instance, I want to use this proof to show, or use this theorem, I should say, to show that the function f of z equals e to the z is entire. So, somebody refresh my memory. What does entire mean?
Everywhere differentiable.
Yeah. In other words, differentiable everywhere in the complex plane. Turns out we can use this theorem in order to prove that. So first of all, let's take f of z equals e to the z and break it up into its real and imaginary components. So, oh, excuse me, I just looked at the packet and realized I should have written g of z. My bad. So how do we find the real and imaginary components of e to the z?
Would it be e to the x plus iy?
Okay, split it up into e to the x plus iy.
You could. That should be yeah.
I'm on board so far.
Yeah, I was about to say something else, but I realized that was not gonna work.
I'll do you one more. We can split it up into e to the x times e to the iy. So what?
Euler,
What does that give us?
e to the x times the cosine of y plus the I times the sine of y.
Indeed. Which we could write as e to the x cosine of y plus I e to the x times sine of y.
Why do we have to use Euler?
Because otherwise we're getting the expression into a single real and imaginary piece is a bit challenging.
Oh, it's kind of like using going from polar to standard form,
Essentially, yeah.
right?
Writing e to the x is just a real number, but e to the iy actually has real and imaginary pieces to it. So without using Euler's formula somehow, taking e to the iy here and getting it into real and imaginary pieces, pretty tough. Dare I say impossible. So with that in mind, what's our u of xy and what's our v of xy? Ginger, what's our u of xy?
E to the x cosine y.
E to the x cos y. And Gary, how about our v of xy?
That'd be I e to the x sine y.
Incorrect. Don't include the I.
Oh, yeah.
Yeah.
Size.
In order for v itself needs to be a real function that's just getting multiplied by I, so we're just going to get e to the x sine y for that. All right, let's take our partials. Oh my gosh, let's hope you remember how to differentiate trig functions. Katrine, what's del u del x going to be?
E to the x cosine of y.
Oh, that one's pretty easy. Cosine y is just a constant multiple. Derivative of e to the x with respect to x is e to the x. But Katrine, how about del u del y?
Negative e to the x sine of y.
Bingo. You get e to the x times negative sine of y, which is negative e to the x times sine of del v del y?
B?
Is there another Caleb in there?
Okay. B x cosine of y.
E to the x cosine. You said that was like what sounded like some universe. Me? like, you know how to do this. All right. So here's my question: for what values of x and y is del u del x going to be equal to del v del y? Ginger.
For all Z.
Everywhere! Yay! Also incorrect because u and v are functions of x and y, not z.
So for all X and Y.
Del u del x and del v del y, hey, they're both always equal to each other because they're both equal to e to the x cosine of y. But Gary, can you tell me where del v del x and del u del y are negatives of each other?
Yeah, they're equal everywhere also, right?
Yeah, everywhere. If you take the negative of del u del y, you'll get e to the x sine of y, which is precisely what del v del x is. Oh hey, wouldn't you know it, the Cauchy-Riemann equations are always satisfied.
But maybe they're not continuous everywhere.
Are they continuous everywhere? Let me ask you this. Are the real functions e to the x, cosine of x, and sine of x continuous everywhere? So,
Yeah. Therefore, their derivatives will also be continuous everywhere.
Yep.
Yeah.
yeah, turns out in this case, we can say that since the Cauchy-Riemann equations are always satisfied, and the partial derivatives are always continuous, here kind of relying on Calc 3 knowledge that things like e to the x cosine y and e to the x sine of y are always continuous functions. I don't really feel like proving that, but they are. What does that tell us, Katrine? From the theorem at the top of the page.
F of Z is differentiable
Differentiable where?
everywhere.
Differentiable at everywhere. Yeah. F of Z is differentiable everywhere. Hence is Nito Magneto. We have proven that f of z equals e to the z is a function that is in fact differentiable over the whole complex plane using the Cauchy-Riemann equations where del u del x always equals del v del y and del v del x always equals the negative of del u del y. And the partial derivatives are always continuous over the whole complex plane. So thus, our theorem tells us f of z has to be differentiable everywhere.
But it's entire, which is what that means, right?
Yeah, which is just, in other words, entire is the fancier way of saying that. All right, so our derivative function is differentiable everywhere. Any questions or comments about how we showed that? If this is a homework or exam question, I'd be okay with something like that. You just saying it's continuous everywhere, except for number 2 on homework 5, which is not, which they're not continuous everywhere.
Even though the Cauchy-Riemann is satisfied.
Yep.
It's still not.
Yep.
Differentiable everywhere.
And I mean, it's a little bit of a convoluted function too, which it needs to be because most simple functions that satisfy the Cauchy-Riemann equations are going to have continuous partials everywhere. Like the one I give you, I forget exactly what it is, but it's a piecewise function. I'll tell you that. All right. What is our derivative? Would anybody like to guess what the derivative of e to the z is going to be? You think it's just like the real exponential, the derivative of e to the z is e to the z, just like e to the x's was?
My
E to
best
the
I
guess.
feel like it can't be that easy though. It's a complex number, so it's always some tricks they're doing.
There's always some tricks. All right. How can we find what the derivative is? And please don't say by taking a limit as delta z goes to 0 of e to the z plus delta z minus e to the z all over delta z. Because if we have to do that, I will cry.
I think we can use our partials.
How so?
I'll leave that up to
You, wow, do we have a nice formula for what f prime of z is anywhere on any of the 3 boards in this classroom that use the partial derivatives?
So we'll have del u del x plus I del v del x.
Oh, hey! Wouldn't you know it? If the function's differentiable, you can actually find what the derivative is just using that. There's a reason why I left it there with a box around it. Yeah, so we could take f prime of z is going to turn out to be equal to del u del x plus I times del v del x. You could also, if you go back to the Cauchy-Riemann equations, you could also do negative I times del u del y plus del v del y would also give you the same result. In fact, those being equal is what gave us the Cauchy-Riemann equations. So what are we going to get? Derivative is going to be e to the x cosine of y plus I times del v del y, so that's plus del x plus I, oh, no, I just can't read my own handwriting, that's an x, plus I times e to the x sine of y. There's our derivative. E to the x cosine y plus I e to the x sine of y. Is there any way we can simplify this?
E to the x times parentheses cosine y plus I sine y.
Oh, okay. Yeah, we can write that as e to the x. You can factor out an e to the x and write it as e to the x times cosine y plus I sine of y.
We can convert it from polar form
Ah,
into polar form.
okay.
So we'll have e to the x times e to the iy. Yep. And then we'll have e to the x plus iy.
Which is just changing z to x plus I y e to the z.
Okay. Alright.
It actually is that simple. The derivative of e to the z is in fact e to the z, using our sort of partial derivative formula. No tricks on that one at least. So yeah, if you know what your partials are, partial derivatives of the real and imaginary pieces, you can use this formula or the other one we came up with to actually find what is your formula for f prime of z.
What was the other one we used?
The other one we used is, what? This is the one I always forget. Negative I del u del y plus del v del y.
Is that in our packet?
Yeah, that's the one. That's the formula we got by letting delta z go to 0 vertically when we were proving when we were deriving the Cauchy-Riemann equations.
Yeah.
This is the one we got from letting delta z go to 0 horizontally, and then where we got the Cauchy-Riemann equations from was just setting these two expressions equal to each other. But the fact that these should give the same thing for a differentiable function means either one of them could be used to right here. In fact, if we use the other one here, if we had taken negative I del u del y, we'd have negative I times negative e to the x sine of y plus del v del y is a plus e to the x cosine of y. And we get e to the x times cosine y plus I sine of y equals, wouldn't you know it, e to the x, e to the iy. We would have gotten e to the z using the other one as well. The fact that our function is differentiable means these two expressions should always give you the same thing. Questions, comments, concerns? All right, activity time. You know, to celebrate the end of week 1, I'll let you all pick your own groups today. I want 2 groups of 2.
I mean, we could do the
Sure.
one permutation, okay.
Real
Just say
analysis
one
versus
permutation.
I just.
Yeah.
Real analysis versus non-real analysis?
Yeah.
Real analysis knowledge isn't as important for today's activity as it was for, or as helpful for today's activity as it was for yesterday, so I will allow this. Alright, so these are our 2 groups. Alright, here's the activity for today. I'm going to give you, this one's actually, I think, a little bit more straightforward than yesterday's. I'm going to give you a function, f of z, and you know, it's a pretty simple function. It's f of z equals x cubed plus 3x y squared minus 3x plus I times the quantity y cubed plus 3x squared y minus 3y.
A simple function.
I mean, it's a polynomial. It's pretty simple, like, relatively speaking, compared to something like if I had given you something with trig or logs or whatever. There's a lot of terms, but they're all really easy terms.
Yeah.
Your job is to tell me where is this thing differentiable, and also where is this thing analytic. Remember, analytic means differentiable at a point and also in some open neighborhood of that point. Have fun.
Well,
Sarah, as a former real analysis student, I'll let you work in Ginger and Katrine's group for today.
Okay, what do we do?
well, start by
Oh, and you also need to tell me what f prime z is.
guess we're writing in yellow.
Perfect.
No, I mean, y'all can have this piece of chalk if you'd like.
Let's be different.
If you want, y'all want to be yellow, go for it.
Okay.
You want yellow belly.
I feel like it won't be hard to figure out where.
We gotta figure out what.
Yeah, we should just start with the
Yeah,
first
well,
one,
she
which
could,
is like,
yeah.
right?
Yes.
Okay, so we have u
We gotta figure out
x
u,
y
u, x, y,
equals
X cubed
Wouldn't,
plus 3xy squared.
X, Y, just be the first
Minus
part,
3x.
parentheses.
okay,
Yeah, that
and
had the I.
then
Y cubed plus 3x squared y. Minus 3y.
Y'all are working on that. I will be back
So-
in just a second.
so
Del u del x will be x squared
plus
y squared
plus 3
the y
will 6xy.
6x.
plus 3y squared.
Six
Six
x
x,
y.
y.
Del y.
6xy.
Yeah.
Y 3y squared plus 3x squared. Minus 3. Cool.
Okay, so now we need to set this one and that one equal. Is that what
Yeah,
you're doing?
I have it in my.
Oh wait, no, it's right above it. du dx equals dv dy. And then, okay. Well, this is true every, oh,
When x equals y.
wait.
With a
Yeah.
y.
Just,
Oh.
yeah, do you wanna just write it
Yeah.
out?
So, del u
Y.
Oh, yeah.
That's why I said it consisted of all the
plus
elements.
del y
Cause case?
Plus.
Or when x and y equal 0.
Are those the only cases?
Yeah, right.
I think so.
Well, these look really similar.
We could like work it out, like just.
I think 3x squared plus 3y squared minus 3 is equal to 3y squared plus 3x squared minus 3 at more places than those.
Yeah, du
Well, I guess it's just.
Hence, you don't need 3x squared equals 3y squared or 3y squared equals 3x squared individually. Those two expressions.
dx. Well, actually, dy. Wait, no. This is 3y.
Okay, wait, let's just,
That's the next square.
let's just.
Well,
work it out. 3x.
They both have 3x squared and 3y squared.
Okay.
Oh, yeah, yeah.
Factor out
there,
square
okay, there it is, yeah.
Yeah,
We would get x squared plus y squared minus 1.
yeah.
Okay, so these.
Oh. So it's everywhere.
Okay.
Yeah, literally everywhere. They're the exact same expression. You just reordered the first two terms.
Yes.
Oh.
That
Yeah.
makes sense.
Okay. Cool.
That's-
Yay.
That Cauchy-Riemann equation's everywhere. But the others need everywhere.
Okay. And then the other ones are always equal.
No, because it's negative of that
Oh.
one. So it, wait, so,
You're right.
Easy to mix up these variables a little bit like that. I know I've done it.
So, negative xy equals xy.
So then 6xy is equal to negative 6xy. Yeah,
Which
it's differential.
could be true if x equals negative y, wait,
No, when one of them equals 0.
true. So either,
Like, we could have negative x equals x. Or negative y equals y.
xy equals negative xy.
well, but when you just get like negative 1 equals 1 and both of these we simplify down.
Well, if one of them equals 0, then it.
Oh,
Weird so
okay.
far.
So either x or y
That's
has to
good.
equal 0.
Mhm.
Right.
Alright,
So when,
When x equals 0 or y equals 0.
oh, sorry, so we need for F. What's
Okay.
the
okay,
F
So along our real or imaginary axis.
yes.
Okay.
Yep. Or that origin.
We got a thumbs up.
Okay, cool.
Z
So-
is
Now what?
d dx.
So you know that it's, I think it's only differentiable where those equations are satisfied. Potentially.
Yeah.
Well, what has to be true about x and or y in order for those two?
They're all polynomials, so they're all continuous.
Oh, I see. Oh, yeah.
Please.
It might help to try adding 6xy to both sides of that.
12xy.
So continuous
What does that say about x and or y?
would only be continuous then along the two axes because that's like the limited condition.
Basically, x is to be 0 and y is to be non-zero.
So since,
So
It
it's
could both
not,
be 0 in this case.
Oh, yeah, they do.
Yeah, because they're, it's not a fraction, so.
Yeah,
Okay,
the-
so
the-
differentiable.
The previous problem, they couldn't both be 0 because then you'd be dividing by 0,
Yeah,
but we don't have anything like that going on here.
yeah.
Nice step.
that's, so we
That's
will
our only
have
condition. Is x equals 0, yeah.
f of
Yeah,
x is
that's- yeah, it's-
differentiable
it doesn't-
at
doesn't change with the,
when
the other one.
x is 0 or y equals 0.
and then.
I got those nice pictures made it through the first full week of class.
yeah. Okay.
Okay, so now we have to find out what f prime of z is using
I'll
that
just.
equation. So f prime of z equals, equals d u dx plus I times d dx.
It's del u del x
Oh, I
plus
guess-
I times del v del x.
Okay.
Is the formula we found earlier.
So then it would be
Okay, that means that.
3x squared plus 3y squared.
Wait, where's that on the,
It's the one I have boxed up
minus
there.
3.
oh, the top left? Oh, okay, yeah, I wrote that,
Six.
I would change
Or
that
sorry,
to-
plus 6.
There are two del x expressions or
Alright,
two
plus
del
y
y
plus 6y.
expressions for finding f primes.
6xy?
And then I don't think we can, well, we could factor out a 3, but in,
You're not going to be able to simplify this super easily.
so we can just leave it.
I would leave it.
Okay, great.
I'll put it to you, let me rephrase. This one does not have it as you can write it as an expression in terms of just z like we were able to do up there.
Okay, cool. Alright, so then we need to find all values of x at which
That parentheses
f of x
part.
is analytic.
So
And
that.
then is our answer different?
How is
Yeah,
it?
yeah, that's true.
E del x is just 6x and y.
I don't think it's ever gonna be analytic. Right? Because if it's just along our axes,
Yeah, then any,
then any disk is gonna include points that are not different.
yeah.
Just 6x y.
I was just thinking, oh, I see.
Yeah.
Because it's like, I feel like it's kind of similar to
Nice job.
boundary.
That's the, that's
That's
it.
it,
You
right?
know?
That's it
Yeah.
right there.
Yeah.
That's-
It's like an edge.
That one doesn't
Like
have a nice
everywhere is
expression in
an
terms of z
Yeah,
like
yeah.
Eve the z one did.
Yeah. the-
Cool.
I was looking for the simplified.
Yay.
Amazing.
Done.
Find all values of the.
Nowhere analytic, what does that mean?
F of
It
Z
means
and-
that all of our points where it's differentiable are on axes
This can be read
and just on the axes.
Okay.
So any disk you draw is gonna include points that are on an axis, which are
That point's different.
Every point is some open
Gotcha.
neighborhood of z naught. Neighborhoods.
Yep.
Like if we
Differentiable
made a
of-
disk somewhere
differentiable on a bunch of points, analytic nowhere.
around,
Yep.
Jeepers creepers.
Yep.
some open neighborhood.
Once now, I'm gonna give them a couple more minutes and then we'll talk.
Okay, sounds good.
As well.
And you all probably get out like early today,
Very, very nice.
so I'll start after.
We do an example, we reload this.
I don't think we had like,
We're all looking at a second part.
yeah, we're trying to figure out how to make so.
So-
Points you know is arbitrary. right?
Yeah, so so the question is, are there any points where the function is differentiable in an open neighborhood of that point? It might help to try and graph out this set right here. The set you found of differentiable points from part A. So if x is 0 or y equals 0, what points in the complex plane does that mean?
Actually, I'm not gonna write, I'll try to use the little C as a straight
As
edge.
an axis.
Oh,
Yeah, try to use that as a straight edge.
yeah, that's
That's not gonna work.
I do not recommend that, yeah.
Alright, so, X equals.
So that means the real component
Either the real component is 0 or the imaginary component is 0.
is 0.
Or potential, or both.
So there has to be a point on the actual quality axes.
Yeah, I think it's just gonna be along the axes where you have differentiability.
That's what I was, yeah.
Oh yeah,
Cause if X is 0, then,
except for the,
Can't.
except for the origin.
yeah, except for origin, yeah.
I think including the origin.
Oh, it can?
But the function's not defined in the origin.
It isn't?
Oh no, I'm thinking about, I'm thinking about the denominator thing.
Function's a polynomial, those are defined everywhere.
There, yeah, you're right, it's a
It's
polynomial.
like how I get
That's
my
the-
It can only be differentiable
So you don't
On
need
the
to call together then?
No,
Yeah,
I should
either-
correct this one.
like this.
I just have this one right now because one of my friends is a deadly and she can't touch it.
You can just say, I mean, you know,
Do you want me to say it abroad, it's not for the Chinese?
Yeah. either right up on the
Yeah,
axis.
she's like texting me all these pictures and I'm like.
So here's my
I'm like so
If your
jealous.
function
You
only
see everyone
differentiable on the
do that,
axis,
and I'm
are
like,
there
Look at
any
this picture she
points
sent me this morning.
where you can find an open neighborhood of differentiability?
I wanted neither. She was like followed up shortly after by an espresso.
It just looks so fun.
Not all of the
And then,
points
like,
on
the
this would
CSP.
be differentiable.
So where's your
Everything
function analytics
connects.
then?
Oh yeah, that's right.
Yeah, so I'm like, literally everyone's like in Europe living their best lives.
I mean, only, I guess,
Well,
locally it would just be on the axis, but other than that, it would.
Were you just thinking this for
Differentiable on the
fun?
axes is an analytic.
Yeah.
If you have a point on the axis.
I mean, I wanna do
At all,
computer
right?
science.
Yeah.
I mean,
Yeah,
yeah,
that's like
yeah.
a lot of
Okay, so like neighboring points on the
I think it's
axis,
just really
even if it's
important.
inside of this, don't count.
It is
It's
actually.
important
Well,
to me to.
They'll count, but
graduate happy.
you need your function to be differentiable everywhere in your
It's
open
actually
disk.
surprisingly
And it would just be
useful, like-
what's on
Yeah.
on the x-axis
Okay,
that would be
so my
differentiable.
fiance.
No matter how small an open disk you take, you're always gonna get points
That's
off.
right.
Does like
Okay.
stuff with, well, he took a class where they did stuff with
good.
antennas.
Assuming
And I was like
epsilon
telling
greater
him
than
like the
zero.
stuff.
Assuming epsilon is greater than zero,
He
yes.
uses all of
Which-
like that stuff.
Epsilon's always gonna be
Like,
greater than
distant
zero.
antennas. It's so interesting. But he also was like, oh no.
Alright,
Actually, every single.
alright, I think groups are ready to present. Sorry to cut
Oh
short
no,
this
you're fine.
conversation.
Just how every single function apparently can be a cosine and sine combined. Is that true?
Oh yeah.
Every nice function can be.
I remember hearing
Really?
that in like an applied setting.
Yeah.
Ask Dr. Webster about that. He can tell you more.
Cool.
Because those cosine and sine show up a lot in differential equations and
Yeah.
you have to deal with it. I mean, you could have horribly nasty functions that don't, but most nice functions. Anywho, let's want to hear your all thoughts on this one. So, Caleb and Gary, what are your thoughts on how to find where this function is differentiable?
It must satisfy the Cauchy-Riemann equations, assuming that the partials would actually be continuous themselves, which they would be because it's a polynomial.
Okay.
And so we calculated the partial derivatives, and you need del u del x to be equal to del v del y, which they are, and the negative del v del x or the other one to be equal to del u del y, which would work as long as either x or y are both at 0.
Okay, so along the axes.
So along the axis, yeah, is where it's differentiable.
Interesting. So, other group, where is it analytic?
We said that it's not analytic anywhere because like at any point along the axis, if you draw a disk around it, it's gonna include points that aren't on the axis, which is not differentiable.
Okay, there's no way to take an open disk of a point on the axis and only contain points on the axes.
Exactly.
Holy smokes. So here we have a different function that's differentiable at a lot of different points, infinitely many along the axes,
It's never analytic.
but analytic nowhere, which, as we're gonna see next week, is gonna have some drastic consequences for that function, especially once we start trying to do integration with it. Holy moly. Alright, nice job today. I'm gonna let y'all go a little bit early, because I think this is a good stopping point. When we come back on Monday, we'll have one more, what I'll call Calc 1 day, where we're gonna be looking at different types of functions like complex cosine, complex sine, complex logarithm, and see how are these functions similar to their real equivalents, how are they different from their real equivalents, and see if we can compute their derivatives along the way. But yeah. Hope you all have a good, what would this be, like a spring break equivalent, 2 days off, that's like 2 weeks off? Have a good spring break. See y'all on Monday. And then on Tuesday, we'll move into the Calc 3 portion of the course and start talking about parametrization and integration.
Or we're doing Calc 3 before Calc 2.
We are just be mixing things up.
Yeah.
And by Calc 3, I mean like parametrizing things, integrating, and Calc 2 will be the last week of the class where we'll be looking at a series. We actually need some of the integration stuff to help us with some of the series stuff, so it actually does make sense to do the Calc 3 stuff before the Calc 2 stuff, even if it doesn't feel like it should.
Awesome. All right, thank you, Dr.
Thank you.
See y'all later.